Welcome back. So we continue our discussion on solution methods that can be used for discrete location models, which we formulate as mixed integer programming formulations. In our previous lecture, if you remember, we talked about complete enumeration solution method, which simply means that trying all possible alternatives, and we concluded that the total number of alternatives that you need to evaluate increases very rapidly with the number of candidate locations. Even with 50 candidate locations, the total number of alternatives that you need to try is 10 to the power 15. Okay, so this is a huge number. Of course, you cannot do it by hand. You need to use computers, because the computers are fast. But still, even with the fastest computers, as the number of candidate locations increases, this will take time. And how much time? It will not take seconds or minutes. Sometimes it will take hours or weeks, even with the fastest computer. And even if you continue to increase these candidate locations, it will take years, even years. So this complete enumeration is a solution method that you can implement only if the number of candidate locations is less. Otherwise, it is not possible. Then it means that we need some other methods. Okay, what are other methods? Since our formulation is a mixed integer programming formulation, we can use the solution methods developed for these programming formulations. And if you go back to your operations research background, operations research course, you will see, you will remember that the main solution procedure that we learned for mixed integer programming was branch and bound and branch and cut, or cutting plane algorithms embedded in the branch and bound procedure. Okay, and usually if you use a commercial solver like Cplex, Lindo, Excel solver, Groby, any other commercial solver, they are implementing these solution methods, branch and bound and branch and cut algorithms. Actually, these solvers and these solution procedures guarantee the optimality of the solution. So the solution that they provide at the end is for sure optimal. But the thing is, still they are faster than complete enumeration, definitely faster than complete enumeration, because they are investigating or evaluating the solutions in an intelligent way. They are not evaluating all solutions. They are cutting some branches in the branch and bound algorithm without even evaluating them, understanding that the optimal solution cannot be on that branch. Okay, so therefore mixed integer programming solution techniques, these branch and bound, branch and cut algorithms, are faster than complete enumeration, but it is still not enough to solve larger problems with too many candidate locations. Therefore, we need some other algorithms. Look, we need to solve this problem, right? That's for sure. We need to solve it. And for that solution, you cannot wait for years. You need that solution now. And if someone tells you that, okay, if you want the optimal solution, sorry, you need to wait for 2 years. That's not fair. You cannot do it. You need that solution now. Then maybe you will tell, okay, the optimal solution is not necessary for me. Just give me a solution that I will use, that I can use. Okay, so that is, we can develop or we can use heuristic algorithms for that reason, for that purpose. Heuristic algorithms are algorithms that provide good solutions, but that does not guarantee optimal solution. Be careful with this statement. I'm not saying that they don't give optimal solutions. They can provide optimal solutions, But the thing about heuristics is you don't know if that solution is optimal or not. You know that it's a good solution. Maybe it is the best solution. You are unaware of it. Okay? And there are many different types of heuristic algorithms. You can implement any one of these algorithms to solve your problem. One of the easiest algorithms that you can develop for any problem is so-called greedy algorithms. Greedy algorithms are these type of algorithms in which they select the best decision at each step. So, for example, if you want to, let's say someone took you to a, let's say, region that you have never been before, and in that region, in that area, let's say, or field, now there is a fog, so you cannot see your around. You can only see one step around of yourself. Okay, and the thing is, you want to climb up the highest hill on that field. Then how can you do this? How can you find the highest hill? Because of this fog, you cannot see anything. So what you can do is, you just look around yourself. You see that on the ground, if you go to your left, it is flat. If you go to your right, it is climbing down. If you go forward, you see that it's climbing up. It's steeply climbing up. If you look at your back, you see that it's climbing up, but not that steep. So what's your decision? What will be your decision? In greedy algorithms, you select the direction which increases the most. Okay? Then what you do, you make one step on that direction, and then look around yourself one more time and find the direction which increases the most, and then make one more step. And by this way, after some time, you will reach to a point where, if you look around, none of the neighbors or none of the directions is increasing, and you will assume that you are at the top of a hill. But the thing is, because of the fog, again, you cannot see anything. That hill can be the highest hill in that field, or that one can be the lowest one, but definitely you know that it is a hill, okay? Because none of the directions around you is climbing up anymore. So this kind of an algorithm is greedy, because at each step you are selecting the direction which increases the highest. Does it guarantee optimality? Of course not. Maybe if you go in one direction which is climbing down first, but later on, after some time, it will climb up to the highest hill in that region. You cannot know of it, but we feel that if we move towards the best direction, we assume that we will find a good solution in quite short time. That's the main idea of such greedy algorithms. Okay, this is one type of algorithm. Another algorithm, you can use Lagrangian relaxation heuristics. This is relaxation type heuristics. What does it mean? You take your mixed integer programming formulation. Okay, you find the constraint which makes your problem complex, the hardest constraint, and you relax that constraint. Instead of writing it as an object, as a constraint, you move it to your objective by a technique called Lagrangian multipliers, and then you try to solve your problem using this relaxed mathematical model. So it's a mathematical model based heuristic algorithm. Another type of heuristic can be a local improvement algorithm, in which you find the solution. You have an initial solution, and for that initial solution, by trying to perturb, by trying to make changes on that solution, you try to improve its value. Okay, so when we for example, move to quadratic assignment problem, we will learn an algorithm or we will solve a problem using these local improvement algorithms. Another type of heuristics is called meta-heuristics. And inside meta-heuristics, you can find a lot of different heuristics. Tabu search, genetic algorithms, simulated annealing, particle swarm optimization, ant colony optimization, artificial neural networks. All of these kind of algorithms, you can count them under meta-heuristics. The main idea of meta-heuristics is this: you start from an initial solution again. In, for example, tabu search, in simulated annealing, you have one initial solution. From this initial solution, you find a neighbor of it and jump to that solution. And for that one, you move to another one, step by step. At each step, you find a new solution. Okay? And you try to improve your objective function value in these steps. And the thing is, sometimes when you start from this solution, you move to a better neighbor. The objective function value is better, but sometimes it is not good, but still you go to that neighbor, because later on when you find the neighbor of that neighbor, then it will be much better than yours. So let me explain it with such a graph. Let's assume that this is a function that we want to maximize. Okay? Then, for example, we started from here. Of course, it is better when you consider it in 3 dimensions and etc. In 2 dimensions, it is a little bit more straightforward. But the thing is, okay, let's assume that we start from here. Or I will go to this one. Let's assume that we start from here. It will be a better representation. Okay, so this is my current x value, and this is the function value. And what I want to do is I want to find the maximum point. Actually, I see that the maximum point is here, but again, remember my story. Now you are in a field with a fog that you cannot see your around, what's around you. Again, in this shape, we see that this is the maximum, but actually you don't know that is a point at all. So what do? You look at the neighbors of this solution. So you can move in this direction or in that. If you move in this direction, take one step, take another step, take another, you come to this point. And when you are at this point, you see that if you go to this direction or back to that direction, you are not improving your objective function. Okay? So then you can make a decision and stop here. And if you stop here, it means that you find a local optima. This is local optima. It is optima. We call it optima because the neighbors of that solution is worse than this one. There is no better solution, better neighbor. But we call it local optima because maybe somewhere else there is a better solution. You don't know it. We only know that it is the optima in its closest neighborhood. Okay, then this is how local improvement algorithms work and stop. Okay, local improvement algorithms stop at this point. But meta-heuristic algorithms do not stop here. They continue to search. Okay, we are now here. How can I search? Meta-heuristic algorithms allows you to make moves which are not improving your objective, with the hope that later on that value will start to improve and it will allow you to find this point. Okay, so this is the idea, usually the idea of meta-heuristic algorithms. But remember, there are many factors that affect the performance of these algorithms. For example, if we haven't started from this point, but we started from here, then if you implement local search algorithm, you will come to this point, right? And it is the global optima actually. So the starting point, where you start from, is important. On the other hand, how do you stop is important. If you stop as soon as you find a local optima, then it may be a worse solution, a suboptimal solution. But if you continue, then you can find a better solution. But of course, look, if you started from here and found this solution, but of course, because of the fog, you cannot know if this is the highest hill or not. Then, if you continue to find better solutions, maybe you will come to this point. Of course, you never forget your previous best solution. You still remember this one. You have visited that. So your final solution will not be this one. Don't worry. But the thing is, what happened all the time that you walked through this valley, all the time that you search for a better solution? It's just waste of time. But the thing is, you don't know it. Maybe there is a higher hill over there and you will find it. So the worst thing about heuristics is this unknown. You don't know. And usually there is a trade-off between solution quality, solution quality, how best is your solution. If you find this hill with your heuristic, it is not good. If this is the solution that you find, it is not good. If you find this solution, it is better. If you find this one, it is the best. Solution quality, but versus solution time, how much time you spend on for finding that solution. So there is such a trade-off. If you want to find high quality solutions, usually, good quality means longer solution times. If you want to sacrifice from this, let's say, solution quality a little bit, you can reduce your solution times. Usually this is the case. And of course, why we are interested in heuristic algorithms? Because with complete enumeration or mixed integer programming, you need to spend a lot of time to find the optimal solution. It takes a very long time. The most important advantage of heuristic is time, computational time. And that computational time is important. If you are going to spend, let's say, 2 years to find a solution with heuristic, then it's not meaningful. For 2 years of time, maybe you will work with mixed integer programming. With heuristic, we want to get the solution in a few seconds or in a few minutes, not more. So it means that these two criteria are important for heuristic algorithms, but usually there is a trade-off between them. If you want to improve one of them, you need to sacrifice the other one, and you need to find a balance. And in meta-heuristic algorithms, in order to find better solutions, sometimes you will waste time by going through non-improving directions, but most probably at the end you will find a better solution. And as I told you, with tabu search and simulated annealing, you start from one solution and then you jump to a neighbor. If it is improving, that is good. If it is not improving, it is still acceptable. And these tabu search and simulated annealing have different mechanisms to accept such non-improving moves. Tabu search, as the name implies, forbids the moves for some temporary time or temporary number of iterations. So if you go from 1 to 2, then returning back from 2 to 1 is forbidden for a number of steps, so that it avoids cycling between two solutions. This is the idea of tabu search. On the other hand, in simulated annealing, if a solution is improving the previous one, you definitely go for it. But if it is not improving, then you use a probability value depending on the objective functions of the previous and the next solutions, and depending on that probability whether you accept or reject. And again, the use of such a probability is because to avoid again cycling between the same set of solutions. So you assume that your computer code searches the feasible space to find a better solution, but in reality it loops through the same two solutions all the time. You want to avoid it, and simulated annealing does it with using probabilities. So it is still, there is a chance still to go into loop with simulated annealing. What it is a very tiny probability, and at each new loop, at each new step, that probability becomes even tinier, 0.000001, and simply it means that no chance for such loops. Genetic algorithms and evolutionary type algorithms are a little bit different than these others, because as I told you, in tabu search and simulated annealing, you start from one solution and jump to another solution and jump to another solution. But on the other hand, in genetic algorithms, you have a population of solutions, not single solution, but a number of solutions. Let's say 100 different solutions, and we call it a generation. Okay, and then from this generation you move to a new generation. It comes from, like, the genetic algorithms, it originates in biology. And how do we find new solutions in the next generation? By using a crossover and mutation. By selecting a pair of solutions from the previous generation, you perform crossover and find two new solutions. So these are called the parents, these are called the children. Okay, and from one generation to another, you try to move the best solutions. Survival of the fittest is the key idea in genetic algorithms. And the main difference of genetic algorithms from tabu search and simulated annealing is, at each step you don't have just one single solution. You have a population of solutions. And again, from this generation you move to another one. And the thing is, at each generation, the individuals in the population becomes better and better. Fitting, let's say. Their objective functions are improving, and in the last generation, when you stop, the best solution here, you assume that it is the local optima, or the best solution that is provided by these genetic algorithms. As I told you, these are just some examples, commonly used examples for meta-heuristics, tabu search, genetic algorithm, simulated annealing. And there are different types of algorithms. Usually they are mimicking the nature. For example, ant colony optimization algorithm. Ant colony optimization. So what is the idea? The idea of the ants, an ant colony, finding the food. Okay? So they mimicked this process of finding food by the ants to these optimization problems, and the idea is find the best solution. Best solution means the best food source, you can assume. Okay, by again a set of solutions, and each solution is represented by an ant. Okay, each ant is a solution, and they are traveling around searching for let's say different good solutions or food sources. Okay, so there are, as I said, many different alternatives. Even yourself can develop your own heuristic algorithm, but before that it is better to learn for the others what are the weaknesses and strengths of the others, and then maybe you can come up with your own idea. Okay, now it's time to solve an example problem to, let's say, understand this idea, how we can solve these problems. By the way, this is an uncapacitated facility location problem example although here it is written capacitated, this example is for uncapacitated. What is the problem? It is said that there are 5 customers located at cities from 1 to 5. Okay, so these are the customers. And then there are 5 alternative sites to establish a new warehouse. Okay, but how many new warehouses will be established? It is a question. How many new warehouses? We don't know. So these are the potential sites for the warehouse locations. This table over here shows you the cost of satisfying a customer from a warehouse. Okay, so if you satisfy customer 1 from warehouse A, then the cost is $100, you can say. From B, it is $500. And if you just compare these two values, you can easily say that satisfying customer 1 from A is cheaper than B. So it is better to use A for this purpose. But there is another cost over here, which is called the fixed cost. And if you look at the fixed cost, you see that establishing a facility at site A is $3,000, whereas establishing a facility at B, site B, is $2,000. Although satisfying the customer from B is more expensive, its setup cost is less expensive. And remember how this setup cost works. So we are going to select a number of sites, I don't know how many, maybe only 1, maybe all 5 to establish. If you establish a facility only to A, then you will pay only this cost. But if you decide to establish facilities to A and C, you will pay this one plus this one as the fixed cost. Okay? And you will pay it only one time for an established facility. What do I mean? For example, you establish this facility A and assign this customer 1 and 2 to A. Then what will be the total cost of this one? $3,000 for establishing that facility, plus $100 for satisfying the customer 1 from this facility, and $1,500 to satisfy that customer from this facility. Then what will happen to the other customers? I need to satisfy all demand. So it means that if I established facility C, I need to satisfy these customers from here. And in that case, the cost of that one will be $2,000 for facility C. This is fixed cost of C, and this is fixed cost of A. Okay? And I pay it only one time, not for each customer that I satisfy. If you establish a facility, this is fixed cost for C. If you establish a facility, then you pay it. Even if you satisfy one customer, you pay the same amount. If you satisfy all customers, you pay the same amount. And then the cost of satisfying these customers from here, $1,700 plus $700 plus $800. So if I decide to open A and C and satisfy customers 1 and 2 from A and 3, 4, 5 from C, the total cost of such a solution will be this much. And the question here is, identify to which of these alternative sites should I open a facility, and which customers should I satisfy from each facility. Okay, so this is the question. And if you want to solve this question, again, regarding our previous analysis, if you want to use complete enumeration, since there are 5 candidate sites for new facilities, the total number of alternative solutions will be 31. You need to evaluate 31 possible alternatives, calculate their costs, and select the best one, and it will be optimal. But 31 is a large number to evaluate by hand. Therefore, we want to find not the optimal solution, but a good solution. Okay, so we will use a heuristic algorithm to solve this problem. Let's think together. What can be a good heuristic for this one? So we can use the idea or the logic of greedy algorithms. Okay, in greedy algorithms, remember, we always select the best decision at each iteration, the best decision. Now let me look, how can we construct or develop a greedy algorithm. What I am going to do is, I will assume that initially to establish only one facility. Let's establish a single facility. If I told you, open just one facility, which one would you open? The question is this: which one would you open? And in order to answer this question, you need to calculate the cost, right? So for example, if you establish A, only A, what will be the cost? It will be 3,000, because we established that one. This is the fixed cost. Plus, it will be the cost of serving all these customers from A. So it will be the cost, sum of all these costs, if you only establish A, right? And what is that total cost? 3,000 plus 100 plus 1,500, 2,500, and etc. And if you add up them, it will be $19,900. This is the solution if you establish just a single facility, and if it is A, only establish A. What about B? Let's see. If I establish B, I am assuming that I am establishing only only B, not A. Okay. Now, if you establish B, the fixed cost is 2,000 plus the cost of satisfying the demand of all these customers. So I need to take the sum of all these values. And if you do so, it will be 17,700. Okay, this is the total cost for establishing a facility in B. Continue in the same way. Only in C, if I do this, only in C, the total cost will be the summation of this, which is $9,600. If you establish only to D, then the total cost will be 14,800. And if you establish only to E, it will be 11,100. Then these are the costs if you establish just one facility. Which one will you prefer? Of course, the answer is obvious. Whichever is the smallest, you select that one. So we decide to establish a facility in C. But the question now, and this is the greedy decision. Look, we are not selecting this E or B. We are selecting C. Why? Because it has the minimum cost. It's why we call it the greedy algorithm. But the algorithm is not over yet. Because the question, how do you know that only a single facility will be established? Maybe two facilities, opening two facilities is better. Maybe three is better. Okay, then what do? We say that, okay, the first one of the facilities is C, definitely. Then, besides C, which one should I open? Okay, so I already have C plus the next one. Which one is it? It can be C plus A. I'm going to try alternatives. It can be C and B. It can be C and D, and it can be C and E. So now I am going to calculate the costs associated with these solutions. And how do I calculate C and A? Look, since I established C, I am paying this 2,000, right? Definitely. and since I am establishing A, I am paying this also. Then I am checking each one of the customers, because we said that in uncapacitated facility location problem, the customers, the whole demand of the customers are satisfied from a single facility. So for the first one, which one will you prefer, A or C? The answer is obvious. It is A. Whichever cost is less, you need to select that one. For the second customer, which one will you prefer, A or C? Again, the answer is A. For 3, which one will you prefer? Which one will you use to serve this customer, A or C? And you see this cost is cheaper than this one. So I will select C. From 4, for customer 4, which one? Again, 700 is less than 2800. For 5, which one? It will be 800. Okay, now what is the solution? Establish A and satisfy customer 1 and 2 from A, and establish C and satisfy customers 3, 4 and 5 from C. And what is the cost of this solution? The cost of this solution is simply the summation of these values that I circled. Okay, this 3000 plus 2000 plus 800, 700 and etc. But actually, you can think in a different way to make your task easier for calculation. So I am going to consider the cost reduction. So originally I had only C, right? And I had, when I have only C, I have these costs. Now when I establish A, I decided to move first customer from C to A. Then what was the original cost? It was 1800. What is the new cost? It is 100. Then what is the reduction in the cost? It is 1800 minus 100. This is the reduction by allocating customer 1 from C to A. The same thing for the second customer. If I allocate it from C to A, the cost reduction will be this much. Are there any other cost reductions? Let's see. The third customer, it was on C and it's still on C. The fourth customer, it was on C, still on C, and the fifth one, so I haven't reallocated them, so there is no cost reduction. But there is a cost increase. Why is that so? Because initially I was not paying this fixed cost for A, but now I started to pay that one. And what is the amount of increase? It is 3000. Now the reduction in the cost, if you calculate, is 2800. This is reduction. This is negative, therefore. I mean reduction, you reduce the cost. And the cost increase is 3000. Then, will you prefer this solution CA over establishing only C? And the thing is, since when you look at this, the difference between them is plus 200, your cost is increasing. Cost increases if you do. So you don't select that alternative. It is not good. Okay. Now, I need to try the second alternative. What is that? I already have C, and now should I open B or not? And if I open B, it means that I need to make this fixed cost payment, and then I need to think about the customers. Should I move them from C to B? The first customer, should I move it? Yes, as you can see, the cost is cheaper. For C, should I move it? Yes, the cost is cheaper. The third one, should I move it? Yes, the cost is cheaper. Fourth one, no. Fifth one, no. Okay, then the reduction in cost is 1800 minus 500 from the first customer, 2600 minus 200 from the second customer, 1700 minus 1200 from the third customer. Okay, and what about the cost increase? Okay, let me write it here, increase. It is 2000 because of this fixed cost. And then the change in cost, if you calculate this one, it will be negative 2200. This negative means that cost is decreasing, and this is good for us. We want to minimize the cost, and you can accept this. I mean, C plus B, opening C plus B is better than only opening C. But before jumping into this solution, it is better to check for the other alternatives. Maybe they are even better than this one. Okay, so if you do this for C plus D, the same thing, you see that your cost reduction or the change in the cost is negative 100. It is still negative, it is good, but when you compare this, it is not as good as C and B. And the third one, if you do, the change is positive 3900. And since it is positive, we don't want it. So from here, we see that C plus B, opening C and B, is better. And what is the cost associated with this one, C plus B? Okay, you will add up the costs of C and B. But you don't need to do this. Actually, remember, when you opened only C, your cost was this much. Okay, this was your cost. And when you decide to open C plus B, it will be your original cost minus the change in your cost. We already calculated the change. And it will be 7400, your new cost. And this is better than your previous one. So we improved the solution. Okay? But now we said that we decided to open two warehouses, C and B. But how do you know that maybe opening a third one can be better? So we already say that C and B is opened, but will there be a third alternative? Now I am going to evaluate those alternatives. C, B and A can be one decision. C, B and D can be another one, and C, B and E can be the third alternative. Look, I am never changing C and B. It is fixed now. I am only trying to add one more besides them. And again, what do? Remember, originally I opened this one and this one. These are the fixed costs. Then I allocated the customers 1, 2, 3 to B and 4 and 5 to C. Now, if I decide to open A, I am writing the differences in red color. Okay, so I need to pay this payment. This is fixed cost. Then, should I reallocate customer 1? If you look, the current allocation is 500, and if I allocate it to A, it is better. It is 100. So I do that. What about second one? Should I reallocate? No, because the current cost is less than that one. The third one? No. The fourth one? No. The fifth one? No. Only the first one. And if I do this, what is the reduction in the cost? I am just allocating the first customer from 500 to 100, so the cost reduction is 400. What about increase in the cost? It is 3000. Then what is the change in the cost? It is positive 2600. This is reduction, therefore it is negative. This is increase, therefore it is positive. And the net change is positive. So therefore this is not a good alternative. Okay? Do the same thing for the others, and you will see that in none of them the cost will be decreasing. Okay? Try this by yourself, and you will see that in all of them this change is positive. and because of that you will not be selecting them. And when we identify it, you don't need to try to open the fourth one. We just stop here. Stop. And what is our solution? Our solution is open B and serve customers 1, 2, and 3 from B and 4 and 5 from C with a total cost of 7,400. Is this the optimal solution? We don't know. This is a heuristic solution. Now you can say that, but sir, we tried all different alternatives here. Did we? Let's see. Originally we said that there were 31 possible alternatives. How many alternatives we tried? Look, 1, 2, 3, 4, 5. Okay, 6, 7, 8, 9, 10, 11, 12. We tried 12 alternatives, but originally there were 31 alternatives. We haven't tried all alternatives. Maybe the remaining ones contain a better solution. We don't know it. Secondly, you can say that, okay, we just almost found 1/3 of this. For example, if the total number of alternatives is 1.126 times to the 10 to the power 15, if this is the total number of alternatives, then if we just take the 1/3 of it, it will still be 1 to the 10 to the power 15. And I will say you, no, because when the number of candidates increases, I mean, the ratio is not to the 1/3. With this procedure, with this kind of procedure, the total number of alternatives that you evaluate reduces really in a huge number. You will never try this 10 to the 15 numbers. You may still need to try hundreds of alternatives, but it will never be 10 to the power 15. Therefore, this algorithm is efficient in terms of solution time. Okay, so this is an example heuristic algorithm to solve this uncapacitated facility location problem, and in our following lectures we will be seeing different models and different types of heuristics.